Alright, good afternoon, everybody. Welcome to our first online remote learning class. Happy you're all here. And I just have to say there is a little bit of a delay in the stream versus what I get to see from the chat. And it takes a second. Hi, Serena. Hello, Cole. For example, I just read those, so I'm not sure how much of a delay that is, but I'm working with what I got. What I plan to do for everyone from now till the end of time is to do these sessions. I've chunked them out. Sometimes they'll be a little longer, sometimes they'll be a little shorter, but I'm aiming just for complete thoughts, complete lessons. So sometimes they'll be like 25 minutes, sometimes they'll be 35 minutes. So I'm going for what I can go for. It doesn't matter if you can make the sessions or if you can't make the sessions. Either one is totally fine. The videos will be on my YouTube account for all time. They're not going anywhere. So we're going to start off today by talking about acids and bases. We're going to start with a little bit of an introduction to them. All right. First, we're going to talk a little bit about properties of acids and bases. Acids and bases, we're going to go into each of these properties as time goes on. Acids and bases. Acids react with a base to create salt and water through a double replacement reaction. So you might remember those from the last unit where we looked at double replacements and precipitation reactions, and we focused a lot on checking table F to see whether or not we made a precipitate or not, something that was solid. For acids and bases, we're going to see that when we combine them, when we do our double replacements for acids and bases, we have a salt, so some ionic compound, and water at the other side. And we'll get into that a little later in the unit. A property of acids is that they're sour tasting, so lemons and other citrusy things. If you've ever had a Sour Patch Kid or any of those sour candies, those are made sour by the use of acids, not very strong acids, but acids that are sour tasting. Something we're going to look at a little bit later in the week is the fact that they can change the color of indicators. They're using table M, which when we get to it, I'll pull it up and I'll walk you through a bunch of examples of that as well. Acids conduct electricity. They are electrolytes, so that means they're going to break down into ions in water. They react with metals to produce hydrogen gas through single replacements, which is another thing we're going to look at later in the unit. And they have a pH of less than 7, which some of you remember from living environment or other classes, other middle school science classes. And some of you don't, but either way we're going to get to talking about pH as well. If we look at bases, bases react with acids to make salt and water. They are bitter tasting and they feel slippery, so that's why I took a picture of soap to put as the picture for this slide here. They also change the color of indicators using table M, which we're going to get to. They also conduct the electricity because they are electrolytes. They have a pH above 7, so the opposite of an acid. They're referred to as alkaline, which comes into play when we think about the columns of the reference table. If you remember, the first column of the reference table is the alkali metals, and the second column is the alkaline earth metals. And when we get to looking at exactly what a base is, a lot of the alkaline earth metals and alkali metals react to form bases, which is where the connection between alkali, alkaline, and alkaline earth metals comes from. The last little tidbit on this slide is the fact that they emulsify fats and oils. Emulsifying means to break down and to kind of trap. So when you wash your body with soap, right? Because again, it's not cheese, it's soap. When we wash our bodies, we want to take away all of the fats and oils that have built up on our skin over time. And that's what the bases in soap allow us to do. Again, obviously they're not going to be super strong bases, otherwise they would react with our skin and hurt us. So it's a balancing act between effective enough to get rid of the oils and soaps, but not aggressive enough or not strong enough to get rid of our skin itself. So it sticks to fats and oils, or does it repel them? When you emulsify, it breaks down and surrounds, so it not necessarily sticks to, but also not necessarily repel. It makes the fats and oils able to interact with water by kind of attaching to them and breaking them down simultaneously. Let me see if I could pull up a good picture of emulsification. So I can't find a great picture for emulsification right off the bat, but the idea behind it is, again, that it just makes it able to interact with the water that you use to then wash the whole thing off. So sticking to it would be the better answer. So acids, bases, we have general properties, but we don't really know what they are and what they do. So when we start talking about, well, what actually makes up an acid or a base, we have two theories that we're going to look at. We have the Arrhenius theory, and we have the alternate theory, or the Bronsted-Lowry theory. So we're going to look at the Arrhenius theory first. Alright, so we're still stuck a little bit on the emulsification. Hold, please. Let me see. I'm just going to go back for a second here. If we have where am I? If we have, let's say this is a fat. When we have the base that comes to interact with it, it'll take a big piece, or a big fat molecule, it'll cleave it into pieces. Cleaving it into pieces. And then the base itself, which I'm going to do with empty circles here, will surround. And then when the water comes along, it will wash all of this away, because the water is able to interact with the base because of the polarity of the pieces. Very much like the water surrounding breaking down solvents. Right? The water will come through. Here's my shower. Run, run, run. It'll take this whole thing and just kind of wash it off of your skin. So the water can't interact with the fat or the oil directly because of the differences in their polarity. But the water can interact with the little pieces of the base because of the polarity of the base. So it kind of creates an intermediary for it to attach and then get washed away. Gregory, haven't we done this on the 13th? We started this in third period, but I didn't do it with any of the other periods because there were a huge amount of absences on the 13th. So some of you are seeing this for the second time, but the rest of you are seeing it for the first time. All right. Gonna pause there for a second. Okay, so two questions. So the soap is like a catalyst. We haven't really defined catalyst yet, but in a way, yes, the soap is like a catalyst, allowing for the interaction between the water and the fat. Since the polarity is different, shouldn't the water push the fat away? Not necessarily, because it's stuck to the skin itself, and it will just kind of run over the surface of, like, it'll run along the surface of the water if it comes along here. I'm still on eraser. If I have water coming along, it'll kind of go over and around the fat, but not interact with and push off of the skin. So we need the soap to make it into smaller pieces, surround it so that we can interact, or so that the water can then push the whole thing away. Okay. This is tough. This is tough, friends. I am not used to this quite yet. Are all bases polar? All electrolytes have some polarity to them. Is there more? There is neither fat nor oil in the soap. The soap itself is a base, which again we're going to define in a little bit. When you have my pen again, something like, for example, if you have sodium hydroxide, it's going to break up into Na plus and OH minus, these being polar because they are ions, right? Not shared equally because they're not shared at all, which can interact with the fats surround them, much like we have for pause. Let me finish this thought first. The ions will surround, much like we saw in dissociation, and then the water can kind of move the ions along down the line. Base is more of a characteristic, yes, 100%. Polar versus nonpolar is non-binary, meaning that there is an in-between. You can have different varying degrees of polarity, yes, 100%. And as far as we are concerned, we care much more about polar versus nonpolar in more binary terms, but it is very much a non-binary sliding scale. We don't really learn enough to go into like sort of polar versus very polar versus, like very little polar versus nonpolar at all. But that is a thing that is done in more detail as you go further in chemistry. Are all bases considered soaps? Definitely not. All soaps are considered bases, but not all bases are soaps. Soap is a very light base that then gets that we could use and interact with our skin without it actually affecting or hurting our skin, whereas like something like bleach, never mind, bleach isn't the right word I'm looking for. Ammonia is a base that is definitely not a soap. It really depends on the strength of the base and the pH of the base, which we'll get to probably tomorrow. Are all bases solids? No. Most bases that we interact with are in aqueous form. If you have a solid base, it is very, very concentrated. And then you normally, if you want to make something with it, if you want to do something with a base, you have to dissolve it in water and have a solution of 1 molar, 2 molar sodium hydroxide, something like that. What does base mean? Well, let's actually jump forward to that then. When we talk about what a base means, bases and acids are dependent upon two things, right? First, acids are things that make H plus, and bases are something that make OH minus, meaning that a lot of different things fall into the category of acid and fall into the category of base. Milk, okay, isn't milk a base? Milk is a base. It is a very light base. It is not a very strong base. So the pH of something determines the majority of its properties. Yes, I would say yes. pH is very important in determining the properties of an acid or a base. The stronger the acid, the stronger the base. The stronger the acid, the lower the pH. The stronger the base, the higher the pH, which again is something we're going to do a little bit later on. Exactly 7 is neutral like water? Yes. So the first acid-base theory that we have is Arrhenius's acid-base theory, and he says, as we can see here, right, he says that acids are things that break up and make H plus and some mystery negative thing. And bases are something that make OH minus and some mystery positive thing. Right? The identity of the positive and the negative don't matter. It's really the OH minus that's being produced and the H plus that's being produced. If we have something that breaks down, right, for example, if I have HCl that breaks apart into H plus and Cl minus, the fact that this H plus is there makes it an acid. If I have something like BaOH2 that breaks down into, oh, I don't want, go away, I don't want that. If we have something that breaks down into Ba plus 2 and 2 OH minuses, the fact that these OH minuses are there are what makes this thing a base. Right? So the fact that it's a Cl minus doesn't matter. This could be an F minus or an I minus or an, whatever negative you have isn't really going to change the fact this is what makes it an acid. Same thing here. I could have a Ba plus 2, I could have a Ca plus 2, I could have an Na plus 1. It doesn't really matter what positive I have, it's the OH that makes it a base. Right, so now, questions. Can all liquids be applied to the spectrum? Can all liquids be applied to pH? No. pH depends on how acidic or how basic it is, so pH can only really be applied to acids and bases. Right? Are all acids some form of liquid? No, you can have solid acids the same way you can have solid bases. But if we want them to interact with each other, the most common way to have them interact with each other is to have them in the liquid form and mix them as pouring one liquid into another. Isn't the first ion of each compound a positive? Correct. So something that has an H plus as its first, right, HCl, something that starts with an H, is most likely an acid. And the identity of the second one isn't really important. Whatever it is, right, HBr, HCl, HF, HI, all of those things are acids. Same thing down here. If we look at the bases, NaOH, BaOH2, CaOH2, all of those things are bases, regardless of what you started with. So now keep going with the questions. Why is water the factor that decomposes the base? It doesn't decompose it. It's breaking down into ions, right? We looked at that in the previous unit. So if we had, right, we looked at our positive and negative, positive, negative, positive, negative, that when you put it in water, it all breaks down. It's just like an ionic compound. These are ionic things that are going to break down into the ions. But now we're kind of zooming in on the ones that are acids and bases. If it has both H plus and OH minus, then it is water. All right, which is being said in the chat as well. Very, very intuitive, people, right? If we have OH and H plus, when those things come together, that's going to make our H2O, that's going to make our water. That was a really bad line. All right, but this combination of H plus and OH minus, if it's both, it's water. Scrolling through some questions. If a liquid is not an acid or a base or a neutral, what would it be? It would just be none of the above. You don't have to be acidic or basic or neutral. Yes, you can go to the bathroom. We're looking at dissociation because the solid is dissolving to become ions. Correct, Mona. We're starting with solid acid or solid base. So I would have NaOH solid, and then when you put it into the water, it becomes the Na plus and the OH minus, and the OH minus, according to Arrhenius, is what makes it a base. So, things that... will we still take the regions in June? I honestly have no idea about that. I'm going to say right now I'm aiming for us to. But I don't know what that's going to look like. Would things with both H plus and OH minus but in different quantities still be water? No, we'll talk about that when we get to pH. When we talk about how we measure how acidic or how basic things are, that's going to come into play a lot. How can you identify the charge? First thing is always positive, second thing is always negative. So if I'm looking NaOH, Na being the first thing is going to be the positive thing. Right, this has to be the positive thing, this has to be the negative thing because it's first and second, as it has been in all of our other units, or when we talk about an ionic thing, it's first thing's positive, second thing's negative. So this is really going to be the way that acids and bases get quantified for a long time. It's the idea that acids make H plus and bases make OH minus. Later on, a second set of chemists come along, Bronsted and Lowry, and they say, Arrhenius, you're great, you got lots of good ideas, but I don't think your theory talks about all of the acids and all of the bases. And so they together come together to make the alternate theory of acids and bases. And the alternate theory of acids and bases take the idea of acid and base and kind of just tweak no, I would like to write, thank you, please, 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 please. No, hey, go back. They take the idea of acid and base and they kind of tweak the definition just a little bit. Bronsted, why does he have this slash through the O in his name, is because it's an accent mark. The same way that you have, umlauts or accents in Spanish or Italian. It's just an accent mark. I think, if I'm correct, these guys are either Dutch or Swedish. And that's where the accent comes from. Then, right, so no more OH. What a great question. It's not that there's no more OH. It's that we're looking at acids as things that give up H+, and bases are things that take H+. So what they're saying is that the making of OH- is not the most important thing. They're saying that the OH- isn't what makes it a base. It's the fact that the OH- can combine with the H+. It can accept the H+ to become water. So, it's not a big change for the definition of acid, right? Arrhenius says an acid is something that makes H+, and a base is something that makes OH-. Bronsted and Lowry say that an acid is something that gives up an H+, and a base is something that can take that H+. The big difference being, just like Emily pointed out, right, we're not focused on the OH as much in the Bronsted-Lowry theory. We're looking and watching a lot more about the passage of the H. Who has it? Who takes it? Oh, they're Norwegian. Thank you, Amanda. Super helpful little piece of information. So it's our Norwegian accent mark. Bases do still make OH. Bases make OH. But by definition in alternate theory, the base is not a base because of the OH- it makes, but the OH- is the base because it can take the H+ and become water. If we look at this reaction, I'm going to change my font color again back to red. If we look at this reaction here, both theories are correct, yes. If we look at the reaction, we want to track the movement of the H from start to finish. So if we look, the H starts with HCl. On the other side, it's just Cl-. So this has lost an H from start to finish. NH3 goes from NH3 to NH4+, which means it has gained an H+. And so if we want to track the movement of the H from left to right, the H goes from the HCl to the NH3, which makes HCl an acid because it donated it, and it makes NH3 the base because it has accepted it. Right. If we had the same type of reaction in an Arrhenius acid and base, we would still see movement of H+ from thing to thing. Right, let me see. Right, for example, if I had HCl plus NaOH, I would have the H moving over. It would be a double replacement. So I would have the NaCl with the HOH, meaning the H moved from here to here. It doesn't change our definitions of acids and bases. It just expands the definition a little so that something without OH can still be considered a base. Right? In this case, HCl makes the H+, it gives away the H. The OH- is the thing that accepts the H+, making it the base. So we haven't actually changed the definition of acid or the definition of base. Pause. I need to plug in a charger. So while I'm plugging in this charger, I'm going to look at some of these questions you guys are asking. Alright, so questions down the line. Both theories are correct. Both Arrhenius and Bronsted-Lowry are correct. They're just expanded definitions of each other. So the thing is... Sorry. This charger is being very difficult to plug in right now. Please charge so I can continue teaching. What was I saying? They're expanded definitions. So the Arrhenius definition is the most narrow definition. But as we look at Bronsted-Lowry, they kind of expand the definition to allow more things in. It's not that Arrhenius was wrong, he just didn't have all of the pieces together. Both theories are correct and both theories are talked about and used. It's called alternate theory because they stopped wanting to type Bronsted and Lowry. There's really no reason for it to be called alternate theory other than the fact that they're just writing a simpler thing than Bronsted-Lowry. Is H plus the only proton donor acceptor thing? Well, H plus is a proton. So when we talk about a proton being donated or a proton being accepted, it's the exact same thing as talking about an H plus being accepted or an H plus being donated. Can we identify the acid and base on the left side of the equation? Yes. We have to identify on the left. We're using the entire equation to look at what happens from left to right. So we need to see where the H plus started and where it went. So we need the right side of the equation to see where it went. But if we're looking at identifying what the acid and what the base is, we're looking at the left side of the equation because those are the two things that we are reacting together. Does everything want to be water? And then the resulting comments down the line for that. Water is neutral because it is equal parts acid and base, right? It's 1 H plus and 1 OH minus. Not everything wants to be water, but when we talk about acidity or basicity, right, how acidic or how basic something is, we're looking at how much that balance has been skewed. If it's exactly 50-50 H plus and OH minus, it's neutral. If there's much more H plus, then it's acidic. If there's much more OH minus, it is basic. And again, when we talk about pH in either tomorrow or the next day, we'll be looking at when we look at pH, we'll be looking at that scale and how it gets measured. Am I going to be live for the lesson tomorrow? I'm going to be live with a lesson every day around this time. Things can be neutral without becoming water, correct. Acids and bases both react and mix, correct. Yes, they do. And we'll be talking about actually mixing them and the reactivity that we have with them. Jack, bringing Breaking Bad into the play here. They're decomposing the body. They're using an acid. It doesn't make the plastic a base. It makes the plastic something that can't be reacted. Again, when we talk about reactivity of acids and bases, we're going to look at what things can be reacted with acids and what things can't be reacted with acids. It's definitely not the first episode, by the way. it's been a long time since you've seen the show, I bet, but it's like pretty far in the show there, bud. So NH4 plus Cl and NaCl plus HOH are bases. No. When we look at the acids and bases, I'm going to label them again. I'm going to label them again at the top in a second. We don't label the whole thing as acid or base. We're labeling each thing as an acid or a base. Right? The acid is the thing that has the H plus that it then gives away. The base is the thing that gains the H plus. Right? So if we look, this, and then here on the other side, it has gained an H plus. Right? So it started with HCl, the acid, it went to NaOH, the base. Here, it started with HCl, the acid, and it goes to NH3, the base. You see the change in the H plus, we can track it from left to right. Is there a condensed version of the two, like the combined gas law, or do we refer to them separately? We're going to refer to each of these theories separately, and they will say, according to Arrhenius theory, according to alternate theory, blah, 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 blah. The thing I wrote at the top here is not a single replacement, it is a double replacement. The H and the Na are swapping. It would not be considered a combustion. To be a combustion, it needs to make CO2 and water at the other side, and we do not have CO2 and water, we have NaCl and water. It's not a matter of wanting. So the question is, does everything want to have a balance of a neutral pH? No. The answer is definitely no. When you combine things, it's about stability and reactivity. So H and OH are going to combine together to make water just because it's more stable as water. It doesn't mean that that's what it wants, it's just what's more stable. If you mix equal amounts of acid and base, if you turn it neutral, it is not safe to drink. Right? If you combine, even looking at this top equation, right? You combined acid and base, you got salt and water. If you drink salt water, that's not good for you. Right? So it's not, neutral doesn't mean safe to drink. Right? Neutral is definitely not safe to drink. Scrolling down, H is the only element that we were replacing. For acids and bases, for this unit, we are really, really looking at and focusing on the H plus. Where does it start? Where does it go? Alright, so for Arrhenius, he's talking about making H plus and making OH minus and how those are going to combine together. When we're talking about alternate theory and Bronsted and Lowry, we're talking about who has the H at the start and who takes the H. Right? So NH3 is a base because if we look at it from start to finish, it starts as NH3, it becomes NH4. It has gained an H plus. It is the H plus acceptor, making it a base. Alright, Jack has a good point here, right? The bad part of it doesn't go away. So if we have, just because you've made water doesn't mean that the other thing is magically gone. Right? You don't drink salt water for a wisdom tooth. You're supposed to rinse it around in your mouth and then spit it out. Water is safe to drink, correct, but salt water is not safe to drink. Base gets H plus, acid gives H plus, 100% correct, yes. Alright, I am going to, let me see here. I'm going to leave us actually with this, right? So here's a Plicker question. Here's an example of the sort of things that we will see. When we're looking at this, we want to know which one is the acid. We know that an acid is the thing that gives H+. So we want to see which one of these things has given the H+. So we're looking from left to right. We'll look, I'll use blue to start with for this one. All right, we have HNO3. On the other side, it has become NO3-. It's missing an H+. So I would say that this is the acid. It has lost an H+. It gave it to something else. If I look just to consistency's sake, if I look at the H2O, on the other side it has become H3O+, which means it gained the H+, which would make this the base. Right? So I see them in the chat. You guys are correct. Our answer here is going to be 2. Right? 2 is the correct answer for this. Right? I'm going to stop us here. Tomorrow, when we pick up again, we're going to talk about pH and how pH works. Again, if you can't make these live, that's totally fine. If you just check back in like an hour or an hour and a half, this should just be on my YouTube channel. I'm going to transition us now for the next 15-20 minutes into practice problems and tutoring. Your homeworks, so if you just stay here, I'm going to end one stream and start a second stream for tutoring. You do have a homework. We're going to stick to the same thing that we've been doing, which is one homework a week on Test Wizard. If you are confident, you can follow along on the PowerPoint itself. Come and check back in on things that you're not understanding, or come to the tutoring sessions, which are going to be after these classes. All right? So I am going to, again, stop this stream and start another one. If you want to just hang here for a second, I'll be back to answer more questions soon. All right? Thanks, everybody.